Good afternoon. There is insufficient time to do more than highlight some of the distinguishing points of three cold fusion models. Both Schwinger's and Sinha's model are specific to deuterium, but all three models apply to all forms of hydrogen that may be referred to as hydrons. Next slide. Nobel laureate Julian Schwinger addressed a problem seen in the original presentation of cold fusion. He made a heretical proposal. Assume an interaction Hamiltonian for deuterium pairs, DD, that includes a short-range nuclear potential in addition to that of the Coulomb forces. Next slide. His solution, the interaction of a nuclear strong force with atomic structures, when presented at an American Physical Society meeting, was objected to so unpleasantly that he resigned his membership in the APS. Schwinger's nuclear boost exists only near points of closest deuteron proximity. Hence, it is correlated with phonon-induced motion. The nuclear boost at the lattice level can generate more phonons at deuterium lattice frequencies. More lattice phonons means more lattice motion and greater atomic displacement. Hence, the boost is an increased nuclear attraction that does work on the lattice. Legitimate questions can be raised about his solution. One question involves reversible versus irreversible processes. The dipole charge of each electron-deuteron pair, ED pair, draws an adjacent D or ED pair closer. This is a reversible process. Work is done by the ED pairs in bringing deuterons together. When a deuteron is drawn away from an ED pair, work is done on both the deuterium and on the electron-deuterium pair. So it is reversible. Work is done by phonons and protons and electrons. Work done by a nucleus with its Coulomb potential adjusts its internal charged components and therefore is a reversible action. But in the lattice, it can create phonons and they dissipate into the lattice, and that is an irreversible process. Therefore, at very close proximity, a nuclear strong force can contribute nonlinearly to system potentials, and that is an irreversible process. K.P. Sinha's problem was how to overcome the Coulomb barrier in DD fusion. His best proposed solution was number 2. Deuterium filling a linear defect. This creates a one-dimensional multi-deuterium atom sublattice. The sublattice spacing is not fixed by the lattice. This allows phonons to bring deuterium or deuterons closer together. In Sinha's model, a multivariable Hamiltonian provides results in 3 regimes. At far spacing, the lattice-dominated regime. In between, we have the sublattice-dominated regime. And then the third case is the coalescence regime. This is where fusion actually starts to occur. In the coalescence regime, Closer alignment of electrons means deuterons move closer together. Also, closer alignment of the electrons results as deuterons move closer. The sublattice spacing can shrink to fusionable dimensions. Schwinger's and Sinha's models are combined into a composite model. Schwinger's model may add critical features to Sinha's coalescence regime. Dirac's deep electron orbit model may be needed to explain many results of cold fusion after fusion has begun. It may first be seen during collapse of the linear hydrogen sublattice. In the composite model, phonons allow nuclear potential energy to be sent to the lattice. Energy loss allows irreversible shrinkage of the sublattice. With a fixed lattice versus variable sublattice spacing, the sublattice spacing as well as the atoms can oscillate, enhancing fusion probability. The Dirac deep electron orbit model means collapse of an electron orbit, which mediates changes in nuclear structure and produces local DD fusion. In the composite model, we have a linear H molecule, and we look at the electron probability distribution. When two deuterium atoms are forced together, their joint potential focuses their 1s electrons into a common core, the molecular bond. Note the different scales for the two models, the two axes. When they get close together, the electron distribution shifts and becomes very close to the axis between the deuterons. When more than two deuterium atoms are forced together in a line, their joint potentials focus their 1s electrons into a common core that overlaps all adjacent spaces, not just the space between the two adjacent deuterium atoms. Thus, there can always be at least one electron between two deuterons. Again, note the different scales for the two axes. Normally, a sublattice spacing is fixed to the lattice spacing. Each horizontal line here represents a linear sublattice of deuterons at a specific time. There's only one linear lattice here. We just look at it through time. The fixed spacing vertical dotted lines represent the palladium deuteride lattice spacing. The connected circles represent the deuterons displaced over time from the lattice. Next slide. Good, got it. When the sublattice is not tightly bound to the lattice, we can have a variable sublattice spacing. Each horizontal line represents a linear sublattice of deuterons at a specific time. The connected circles represent the deuterons displaced over time from the lattice and sublattice spacing. A variable sublattice spacing allows deuterons to periodically come closer together than would a fixed lattice. When close enough, deuteron pairs will experience or share their nuclear potentials. In the present view, cold fusion is enhanced in a linear defect. That's from Sinha's model. Electron effective mass is increased by electromagnetic coupling to lattice, again from Sinha. Total potential well of a one-dimensional sublattice can include many items, both from the lattice and from the nucleus. Schwinger's model for dropping below the neutron fragmentation level does not eliminate fragmentation. It only alters the probabilities. DD fusion is dependent on the proximity of the electrons to the linear chain nuclei and time spent in DD tunneling distances. Early in the process, the deuterons are further apart. The longer the time in collapse of linear hydrogen processes, the more prefusion energy is dissipated into the lattice by tunneling lower into the nuclear potential well of the excited state of helium-4. Current research in a separate field gives support for cold fusion models. This is the field of metallic hydrogen, and we have a reference there. But why do we want metallic hydrogen? Electrons are not bound to a particular nucleus. They are free to screen positive charge regions, i.e., the nuclei. This allows deuterium nuclei to get closer together. How do we make metallic hydrogen? High enough temperatures will ionize all atoms. High pressures press atoms together and raise the energy levels. Or we can confine the atoms into linear molecular chains. What prevents hydrogen from becoming metallic? The Pauli exclusion principle is the primary reason. Considering only the ground state, a diatomic molecule fills the ground state. Combining more than 2 hydrogen atoms requires excited electron states. Recent metallic hydrogen computational models available for hydrogen in a linear chain can be applied to cold fusion. At low hydrogen concentrations, the sublattice spacing is dominated by the lattice. Insertion of more hydrogen implies dimerization, which overcomes lattice effects. The hydrogen starts to form molecules, but they're still kept in the linear form because of the constraints. Further insertion of hydrogen implies the metal insulator transition region. This electron band diagram at 2 different sublattice spacings. At large intrahydrogen atomic spacing, for example, R at 2.5 Bohr radii, the 1s orbital is filled, hence no conductivity. At small interhydrogen atomic spacing, for example, at 0.9 Bohr radii, the 1s orbital is almost filled, but a half-full 2s orbital, hybridized with 2p orbitals, provides good conductivity. This figure shows the transition from an antiferromagnetic insulator with a spacing of 2 Bohr radii to a conductor, for instance at 1.4 Bohr radii, with reduction in lattice spacing. Equilibrium spacing for the linear H chain is at 1.7 Bohr radii, and the full metal transition spacing is at less than 1 Bohr radius. In the present status of some cold fusion models, several models have part of the truth. When combined, do they have enough to succeed? Do we have to stray far from known physics? Are present linear H computational models going to work for the cold fusion case in a lattice? Do we know enough to make a breakthrough? We need linear hydrogen, many atom molecules. We need lattice structures to keep hydrogen atoms aligned. We need a crystal lattice that will allow hydrogen to diffuse into and through its structure to feed a linear H chain. Do we need more? Different models for cold fusion are converging to a coherent picture, thus fitting the data without violating present physics or chemistry principles, but not necessarily the attitudes. This may be possible. Do we have any analogy for the composite cold fusion model? Everyone has seen a dipping duck or an equivalent perpetual motion machine. We get lessons from the dipping duck. With no apparent transfer of mechanical energy, the duck overcomes friction and keeps dipping. The small synchronous transfer of thermal energy into the water allows efficient conversion of thermal to mechanical energy. Lessons from the dipping duck as applied to cold fusion. With no apparent transfer of mechanical energy, the nucleus can draw an electron closer and in the process speed it up. Actual energy transfer is through the E field of a Coulomb potential. The nucleus sends energy to and does work on the electron-deuteron pair. This loss of nuclear energy comes from the nuclear mass. The loss of energy and mass of an atom as an electron is drawn closer into a deeper orbit might also be seen in the release of a phonon or photon, again, an irreversible process. How is the nuclear mass changed as the electron moves closer? The electric and magnetic fields increase at the nucleus. The spacing between the charged nucleons and their charged components will increase with the nuclear Stark and Zeeman effects. This decreases the nuclear binding energy and therefore the mass. Two deuterons drawn closer together by a bound electron will both lose mass, and Schwinger claimed that if they come close enough to fuse, the nuclear forces will repeatedly attract the electron a bit closer and lower the nuclear masses to below the helium-4 neutron fragmentation energy level. When a change in nuclear Coulomb potential is recognized as the result of distortion of the charged nuclear components, then the connection between Schwinger's assumption and Dirac's deep orbit electron model suddenly becomes apparent. We've lost the last slide.